All right, so let's take a look at the last part of 4.2. So just as a reminder, what we did yesterday, every problem that we graphed yesterday, the degree in the top was either smaller or equal to what was in the bottom. Just to bring up a couple examples from yesterday. This one, did we sketch this one?
Yes.
Yeah. So what's the degree in the top for that one? 1. Yeah, it's a 1. And the degree in the bottom is a 2. So the degree in the top was smaller than the bottom. If we had done this one, which if we have time we'll go back and do it, the degrees here are equal. Those are the only two kinds we looked at yesterday. The top was smaller or equal to the bottom. Now, today, we're going to look at how to graph rational functions where the degree of the numerator is bigger than what's in the bottom. Depending on how much bigger it is, it can get more and more complicated to do. Okay. So we don't look at ones that are a lot bigger. We're generally going to look at ones that the degree in the top is either 1 bigger or 2 bigger. And as far as actually sketching, we're only going to sketch ones where it is 1 bigger. Okay, so any questions on the difference between what we're going to do today and what we did yesterday? Still graphing, just the bigger exponent is going to be in a different spot. One thing that is going to happen is when the bigger exponent is in the top, horizontal asymptotes go away. You cannot have a horizontal asymptote in any of the problems from part 2 of this section. Can't happen. The only way you can have a horizontal asymptote is when the degree in the top is less than or equal to the bottom. That's the only time you can get a horizontal. The horizontal is going to be replaced with something else today. What the horizontal ends up being replaced with, we're going to call it the EBA, the end behavior asymptote. So when you divide two polynomials, we talked about 2 different ways you could divide them. One of them was long division. Does anybody remember the short way? Synthetic division. Okay. So you can do long division or you can do synthetic division. When you divide 2 things, what do you call the answer that you get? The quotient. And what if there's something left over?
The remainder.
The remainder. Okay. So when you divide these 2 things, you'll get a quotient. Oops. And you get a remainder. After you do division. The quotient is the part that we're interested in. Okay, we are not interested in the remainder. In fact, the quotient is the EBA. Okay, that's what it is. So to find the EBA, that's a new term. We've never said end behavior asymptote. But the way you find it is you just do long division and write down the quotient. The quotient is the EBA. So Q of x is the EBA.
That's supposed to say suppose Q of x and R of x?
Yeah. Suppose Q of x and R of x. Yep. Suppose Q of x and R of x represent the quotient and the remainder after long division. Now, I can't guarantee that the quotient and remainder are always going to be numbers. Usually the quotient has 11. Right? If we can use synthetic division to find the quotient, I prefer to do it that way because it's faster. If we can't, then we have to do long division. just wrote the same thing up above, but a little shorter. The quotient is the EBA, end behavior asymptote. Okay, any question on that? Yeah.
So the quotient is Q of, this is just clarification. Q of X is quotient and R of X is remainder.
Yep. Yep. So I'm going to give you a problem, and the first thing we're going to just try to do with it is find the EBA. Okay, we're not going to sketch it by hand because it's going to be a little bit more complicated than what I want to sketch by hand. But finding the EBA and just writing that down with no picture, that's pretty doable. So here's our problem. It says find the quotient, find the remainder, and find the EBA of this problem. That's as far as this kind of problem would go. I would not have you sketch this problem. I would just have you find what I am asking for right there. All right. So first question, is this a problem that can be done with synthetic division? Or do we have to do long division?
Synthetic.
Yeah, we can do synthetic division as long as the bottom is x minus a number. And technically, even if it's x plus a number, we could rewrite it as x minus a minus number. When we do synthetic, what number goes on the outside? 2. Yeah. Whatever comes after the minus sign, that goes on the outside. What are going to be my numbers on the inside part? 2, negative 4. Yeah, we got to make sure you remember that 0. Okay, the reason we put a 0 is because there's no x term. Okay. Make your line. Right. What's the first thing you do with synthetic division? You drop down the first one. Drop down the 2. Yeah. And then how'd you get that? Yeah, you multiply 2 times 2. That gives you 4. And then you add them up. With long division, you subtract. With synthetic division, you add. And then we repeat it. What's 2 times 0? And then add that column. 0. And 2 times 0 one more time. And then add that column. 3. Okay, so now we have to interpret that and write down the quotient, the remainder, and the EBA. Let's start with the quotient. Remember, that's your quotient, that's your remainder. What's the quotient? I need some letters. Yep.
2x squared.
2x squared. Okay. What's the remainder? 3. And what's the EBA?
2x squared.
Yep, 2x squared. And when we write the EBA, the A stands for what? An asymptote. And whenever we write an asymptote, I told you it always has to be written with what symbol?
Equal sign.
Always going to have the equal sign in there. So the EBA, it's an asymptote, so that means it's an equation. There you go. So the quotient, the remainder, and the EBA. You do not write a quotient as an equation. A quotient is exactly like we did it there. But an asymptote has to have an equal sign.
Is the EBA always y equals?
An EBA is always y equals. The only time it's x equals is a vertical. That's the only time you put x equals. Any question on that? Right, now, let's graph that. Okay, I'm going to type in the original problem. Let's put in 2x cubed minus 4x squared plus 3. And we're going to divide by x minus 2. Okay, and what did we get for an EBA? Y equals 2x squared. Now, because the 2x squared is an asymptote, I want to show that as thin of a line as possible. The thicker it is, the more confusing it is to look at on the screen. So what I'm going to do is I'm going to go over and I'm going to make both of these a thinner line. So there's the first one. Again, it's not necessary, it's just going to make it easier to see. Okay, so I made those thinner lines. I need to set my window. Right now it's set for zoom 6. I just remember that's not going to work. You've got to set your Ymax up to about 30. And I think that's the only thing you need to change. Now, what shape is 2x squared?
Parabola.
It's a parabola. So we're going to see something here that looks like a parabola. Both graphs are going to kind of look like parabolas. There's the first one. And that's the asymptote. Okay, so remember, an asymptote is something you get close to. But do you ever reach it? No. So look at what's happening here. You have that red curve, and then you've got the blue one. As you go further and further to the left, what's happening to the red and the blue? Right, they're getting closer. So yesterday, we had asymptotes, but they were always straight lines. So the graph would be getting closer and closer to a straight line. This one, the graph is getting closer and closer to something that curves. So it's a curved asymptote. And the same thing happens on the right. As you head further and further right, the red and the blue are getting what? They're getting closer and closer as well. But they'll never reach. Okay? It'll just get closer. Right? So that's something you're getting close to, but it curves. That's called a curved asymptote. Specifically, it's a parabola asymptote, or quadratic.
Is the calculator drawer open?
Oh, yeah. Let me, Now, the other thing I want to look at is the denominator. What value are you not allowed to use in the denominator?
2.
2. So, because 2 would cause you to divide by 0, that means your graph has a what at 2? Well, if it had a common factor in the top and bottom, we could have a hole. This doesn't have a common factor. So instead, we have a vertical asymptote. Okay, so there is a vertical asymptote at 2. And you can see that pretty clearly in the graph. If I just put this line at 2. Right there. So basically what's happening is a graph can never cross a vertical. So it's like the blue curve wants to be connected. But at 2, it's like the parabola was cut. And then part of it was bent down. And then the other part of the parabola was bent up. That's what happened to the parabola. It's like bent and it was stretched out. Okay. So as far as what you'd have to do in this problem, that's what you'd have to do right there. And you can check that your answer is right by graphing it and seeing if they get closer and closer. If they're not getting closer and closer as you go left and right, then your EBA is wrong. Okay. They have to be getting closer and closer. Okay, so any questions on how we found the EBA or did that sketch? Okay. All right, so a couple things just to make sure we understand. We've talked about two different things that sound kind of similar. We've talked about an EBM, and we've talked about an EBA. Right? There's a difference. Okay, the EBM, that's easier to find. All you have to do is take the highest degree term in the top and divide by the highest degree term in the bottom. That's what we did in the homework last night. The EBA, you have to do synthetic division or long division. That's the difference. Question on the difference on how you find an EBM or an EBA. EBA, we didn't talk about yesterday because you cannot have an EBA in the kind of problems that we did. Right? EBA is only going to apply when the degree in the top is bigger than the bottom. And that wasn't the case yesterday. For today, we can find an EBA and an EBM, the problems that we're doing today. When we find them, it is possible that they come out the same or they could come out different. It kind of depends on the problem. So if I go back to the one that we just did, okay, I'll come right back to this. If I go back to that for a second. The EBA was 2x squared. What's the highest degree term in the top?
2x to the third.
2x to the third. What's the highest degree term in the bottom? And if you divide them, what do you get? 2x squared. So in this case, the EBM, which is what we just did, and the EBA, which we did with synthetic division, they came out the same. That doesn't always happen. But in this case, it did. And what kind of asymptotes, what were the two kinds of asymptotes we studied yesterday? Horizontal and vertical what? Asymptotes, what shape though? Lines, linear. Okay, they were always linear. In the last example we just looked at, was the asymptote a line?
No.
No, it was a curve. So, if we do the kind of problems that we did yesterday, where the degree in the top is less than or equal to the degree of the bottom, then you always will have asymptotes that are straight lines. That's the kind we did yesterday. If that's not true, okay, in other words, if the degree of the top is bigger than the bottom, then asymptotes can curve. And we just saw an example in the last problem. Now in the last problem, the highest degree in the top was a 3. The highest degree in the bottom was a 1. What's the difference between 3 and 1?
2.
It's a difference of 2. That's why the asymptote was a quadratic in the last problem, because it was a difference of 2. If you had a problem where the highest degree in the top was a 5, and the highest degree in the bottom was a 2, what's the difference between 5 and 2? 3. So now if you did a problem like that, the asymptote would be a cubic shape, like y equals x cubed. The further and further apart the number in the top and the bottom get, the more and more complicated the asymptote gets. A difference of 2 is the most that we ever look at. We're going to look at a difference of 2, and then we're going to do a difference of 1. Now, a difference of 2, did I tell you would have to sketch that or not? Like that last problem? No. When it's a difference of 2, you won't have to sketch it. If it's a difference of 1, yes. And that's what we're going to look at right now. We already did example 6. It was to graph the EBA and show that it was getting closer and closer. So we did that. Let's do... I don't want to do that one first. I'm going to make up. Let's try graphing this. So x squared plus 3x minus 7. And we're going to divide by x minus 2. And to graph it, you do all the same stuff as yesterday. Find the asymptotes. Use the calculator to check a value that's very close to the asymptotes. Like if an asymptote was at 5, check 4.99, check 5.01. But you do the same stuff. Okay, the degree in the top is bigger. I told you that means there are no horizontal asymptotes. So we don't have to worry about that. I do want to look for verticals. Are there any vertical asymptotes in this problem?
Yes.
Yeah, where would it be?
X. 2.
X equals 2. This problem only has one vertical asymptote. The next one we do will have two. Okay, so it has one vertical. Next thing I want to do is find an EVA. That's another asymptote. I know that I'm going to be doing an EVA because the degree in the top is bigger than the bottom. What is the degree in the top?
2.
And the degree in the bottom? 1. So that's a difference of 1. Okay, it's a difference of 1. So it's not going to be as simple as a horizontal line, but it's not going to be as complicated as a quadratic. It's going to be in between the two. So we'll see what that looks like.
What was the vertical asymptote 2 again?
That's the number that would make the denominator 0.
Okay. Thank you.
Yep. Okay, EVA. We can do long division or synthetic. Which one would work here? Synthetic, we could do it because it's faster. So let's do it that way. What would be your numbers on the inside?
1, 3, -7.
1, 3, -7. Okay, bring down the 1. It's 2 times 1.
2.
And 3 plus 2. 2 times 5. And 10 plus -7.
3.
3. Okay, the EVA is your what? Remainder or quotient? Quotient. So, what's the EVA here? Or, well, let me ask this first. How should the EVA always start? Always starts y equals. And what is it?
X plus 5.
X plus 5. That's your EVA. Is that a quadratic?
Nope.
No. So it doesn't curve, but is it a horizontal line?
Nope.
No. Is it a line? Now, what kind of line is it?
Slant.
It's a slant. Okay. It's a slant. And this is going to be called a slant asymptote. A slant asymptote is in between a horizontal and a quadratic. So it's like it's in the middle. It's not as complicated as the one that curves, but it's not as simple as a horizontal. Okay, so I'm going to write that down. It's a slant. You will always get a slant asymptote when the difference between the top and the bottom is a 1. Okay. All right, so we got the EVA, we got the vertical, we got. I think we're good. Let's make a sketch. Okay. So we're gonna need that. Okay. Where was my vertical asymptote? 2. 2? Okay, I'm gonna make that smaller so it's easier to draw. So vertical at 2. And my EVA is x plus 5. So you have to graph that. What's your y-intercept in x plus 5? 5. So put a dot on the y-intercept. And what's the slope?
1.
1. So up 1, right 1. Well, if I put enough dots, I basically don't even have to draw my line because it's already drawn for me. All right. Now what we want to do is check some values near the asymptote, and then check a few values that are on the left side and a few on the right, and that's going to give us our picture. Okay. How are we going to check the values quickly? Using the table. Yep. So the first thing we have to do is put in the problem. Can someone just tell me, because I'm not on the screen there, what was the top? X squared plus 3x minus 7. And the bottom must have been x minus 2. Okay, what's a value that's very close to 2?
1.999.
Okay, so we're going to start out just to the left. 1.99999. We are at negative 30,000. Okay, so basically, where is that?
Negative infinity.
Negative infinity. Way down. What would be a value to the right?
Negative 10. Or
0.001.
What is it?
2.001.
Yeah, 2.001. So just to the right of 2 we're going to be up at 30,000. Okay, so we're going to be way up here. Unfortunately, where the asymptotes cross, we do have to draw in two parts of that like X shape, and the top part is just barely on the graph. So we're just going to do the best we can with that. All right, so we got 2 points. Now let's check some points that have X values in that area. What would be a good X value to check? All right, so we could do -5, roughly -0.5. So 1, 2, 3, 4, 5, -0.5, right about there. Okay. What would be, let's do these in a color where I can see them. What would be another one?
-10.
All right, so we could do -10. And we're at -5.25. So -10, 1, 2, 3, 4, 5.25. All right, so I can see what's happening here. We're pretty much just staying very close to that, going through those red dots. Maybe 2 more points.
1.
Right, so 1, 3. So 1, 3, we're up there. And actually, I think that's enough. So what's going to happen is it's going to stay very close, but then it's going to have to curve at some point, but it can't keep curving and go straight because it runs into the vertical. So it's going to curve and go down, just like this. Okay, so that's what that part looks like. And now let's check a few more X values in that section. What would be another X value we could check? So we could try 4. Yeah, just barely we can do it. So 1, 2, 3, 4. We're like 10.25. If we check 5, we're at 11. So we're up a little higher. So 5 are like up there. So what's going to happen with this piece? It's going to stay close to the vertical. And then as you keep heading to the right, it's going to get closer and closer and closer to that slanted line. That's what it looks like. Let's graph it. If I do zoom 6, you're not going to see anything because the top part of the graph is completely above 10. So let's go up to 25 maybe. For Y, oh, I didn't mean that one. I meant the other one. X backs at 10 was fine. I was going to set it to 25. It's already set to 30, so that's okay. Let's hit graph. So there's the part in the lower left, and that's the part in the upper right. So when you have one vertical and one slant, it always makes kind of an X shape, and you end up drawing your graph in 2 parts of the X shape. And then the other 2 parts of the X shape over here and here, they are blank.
There you go.
Question on that one? Right, so slant asymptote, 1 vertical. Let's try all right, we can try this one. Well, they want us to find the verticals, and the verticals are where what happens?
X.
Okay, so we're going to write them X equals, but how do we find them? We look for what?
Approaching the roots of the denominator.
Yeah, you look for the roots of the denominator, which means you look for where the denominator is 0. To figure out where the denominator is 0 here, it's a quadratic. What do we usually do with a quadratic? We factor it.
X minus 1.
Let's see. Yep. So x squared plus 3x minus 1x plus 3 minus 1 is 2. Perfect. Okay, so now this should tell you how many vertical asymptotes you're going to have. How many numbers make the bottom 0? How many different numbers? There's 2. What's the first one?
1.
So we're going to have a vertical asymptote
X equals 1.
at 1
X equals -3.
and -3. It's going to change how the graph looks quite a bit. But in terms of how we do it, we're just going to have to check some more points on the calculator. Yeah.
Do you prefer 2 separate x equals, or would you accept x equals 1, -3?
Yeah, they're going to be set up as separate boxes on the test.
Okay.
Yeah. Okay, now how do we find the EDA? What do we have to do to find the EDA?
Some long division.
Right, we're going to have to do long division. It looks like it could be kind of bad, but it's not, because they're only 1 apart. So you're only going to have to do 1 round of long division, and then you're done. If they were like, if this was like x to the 5th in the top, and that was an x squared, well, then you'd have to do 3 rounds of long division. But in this case, it's just 1. Okay, what goes on the outside?
The bottom, the denominator.
The denominator. Okay, and on the inside, are we missing any terms?
No.
Yes.
On the top, yeah.
Yeah. So we got to fill in. What do we have to fill in?
0x.
0x. Okay. So now divide the first term on the outside into 2x cubed. What's 2x cubed divided by x squared?
2x.
2x. So our slant asymptote has a slope of 2. We got to keep going to get the y-intercept. What's 2x times x squared?
2x cubed.
That's going to be 2x cubed. 2x times 2x.
4x squared.
And 2x times -3.
-6x.
That doesn't even matter because that would be part of the remainder. What we really are going to be looking at is this x squared. That's the important one. Now, what do we do with the columns?
Flip this side.
Yeah, flip the sign, subtract them. That's gone. What's 7x squared plus or minus 4x squared?
3x squared.
3x squared. And like I said, the rest doesn't really matter, but you can put it. So 0 minus -6 becomes a +6, and then bring down the -4. But the last thing we need to do is divide 3x squared by x squared. 3. That's the EDA. 2x plus 3. Oops. EDA. Okay, 2x squared plus 3. All right, so how do I graph that? What's my y-intercept? 3. And my slope?
2/1.
2/1. So how do I get to the next point using a slope of 2/1?
Go up to right.
Yep, up to right 1. And again, I usually just do it enough times that it looks like you almost have a dotted line. It's good enough. Okay, if you want to put some more in there, put some more in there too. So there's your slant. Where was our first vertical?
1.
So 1 and the second vertical. So this is going to have 3 pieces. It's going to have a left piece, a middle piece, and then a right piece. So we just have to check all 3 pieces. And the way we're going to do that is to use the table on the calculator. All right, let's start with -3. What's a good value we could plug in that's just a little bit smaller than -3? Yep.
-3.001.
-3.001. Yep. So we're at, I probably didn't type in this problem yet. No, I didn't. All right, let's put in the problem. 2x cubed plus 7x squared minus 4. And you're going to divide by x squared plus 2x minus 3. Okay, I didn't say it, but the parentheses are important. Got to put those in. Now, let's put the value Brady just said. Negative 3 gives me 12,497. So that means I'm up where? Infinity. Very high. It's way up. Okay. What's a value that's just to the right of negative 3?
Negative 2.999.
Okay, negative 2.999. And we are at negative 1,200. So way down. Way down. Okay, let's check near the other asymptote. What would be a value that's to the left of that asymptote?
0.999.
Yeah, so 0.999. And we're at negative 1,200. And a value that's just to the right.
1.001.
Yeah, 1.001. Okay, positive 1,200. Okay, so way up here. Now we've got 4 points. We're going to need a couple more x's in this section, that section, and that section. So let's start with the left section. What would be a couple x values we could get in there?
Negative 2 would be something.
Well, negative 2 is going to be in the middle section. Yeah, negative 4 is right there. So we could do negative 4. And negative 4, negative 4. Okay, 1, 2, 3, 4. 1, 2, 3. Right there. And I think that's enough in the left section. Because remember, you got to draw it through those blue dots, and it has to stay close to the asymptotes. So it's going to have to do something like this. It's going to come down, and then it's going to curve, and get closer and closer. Okay, so there's the left. Now the middle, we've got 2 dots on the bottom. Okay, they're not just going to be connected with a straight line. Okay, we need a few more x values in the middle of the asymptotes. So what would be some good x values in the middle?
0.
0, that'd be a good one. So 0, 1.3. There's one. How about another one?
Negative 1.
Okay, we can do negative 1, negative 0.25. So right about there. And I think we've got enough dots in the middle now. So it can't cross the vertical, but it has to stay close to them as long as it can. So it's going to kind of come up like this. It's going to start to curve away from it. Go through those 2. But then it's going to go back through that one. So it's going to have to come back down. Just like that. There's the middle. And now we need some on the right. And for the right part, it's probably going to end up right in there. So what would be an x value that gets me in that section? 3, we could try it. Yeah, that's on the graph. So 3, 9.5. 1, 2, 3. We're about right there. What would be one more?
2.
Yeah, 2. I don't think I could do any bigger. I'm going to go off the graph. 2, 8. So 2, 8. All right. So now I can see what's happening at the top. It's going to come down. It's going to curve. And it's going to go back up. And that's your 3 pieces. So the only time you get 3 pieces is when you have 2 vertical asymptotes. 1 vertical asymptote, 2 pieces. All right, let's see how we did. So window, I got a lot more room on the graph here, so I'm going to set it at 30. Otherwise, you're only going to see a very, very small piece. Well, I could show you what it looks like. So now I set the window exactly to what we see right here. So you see a lot of the left piece. That one you'll see completely. You'll see all of the middle. And you're just going to see a little bit of that part on the right. Right there. There's your sketch. Any questions on that?
How is this going to look in the test? Like, is this something on Edpuzzle that we can do? Or is it like you're going to give us a piece of paper and we draw it out?
So what I would do on the test is, if this was all one question, it would be multiple parts. The first part would be find the vertical asymptotes. There'd be a box to type them in. Then the second part, there'd be a box for the EBA to type in. And then the third part, that would probably be like a multiple choice where you got to match the sketch to the equation. Yeah. Any other questions on that one?
By matching the sketch to the equation, do you mean like
Yeah, you'd have some different pictures as choices.
okay?
Yeah. Yep.
So whatever one fits the bill closest.
Yeah. Yep. But the short answer part of it would be to describe this. I could also ask for the domain here. That would be a short answer. What is the domain there? Yep.
All real numbers except for 1 and -3.
All real numbers except for the ones you're not allowed to plug in, 1 and -3. So that could be another thing I ask for. What if I ask for the range? How far up, how far down, and does it hit everything in the middle? Does it go? What do you think the range is?
All real numbers.
The range is all real numbers. If you didn't have this left piece, then the range would be everything from this number down and from that number up. You would have a gap in the middle. But because of that left piece, it hits what's in the middle. So the range in this problem is all real numbers. So there's still a lot of short answer stuff you can do with this question, besides just drawing.
How did you plug that into the calculator?
The original problem?
Yes.
Just like that.
Okay.
And there was a parenthesis there, but there's a black box. Okay, that example, again, I already told you guys that. That's called a slant asymptote. This might actually be example 8 because I did an extra one. Okay, any other questions on this one?
Nope.
Okay. So then we did that one. We got that one. Okay, let's look at this one. So this one, because it's a cubic in the bottom, a little too complicated, bless you, for us to deal with it by hand, and it's got pretty big numbers. So something like this, I just want you to graph it and tell me a window that you can see everything important. That's all. Right, let's type it in. And we just have to be careful because let's see what happens. It's 2x to the 4th plus 7x cubed plus 7x squared plus 2x and then divided by x cubed minus x plus 50. What kind of asymptote are we going to have here because the degree in the top and the bottom are 1 apart? A what? We're going to have a slant. Some kind of slant. So that's one thing we should make sure we zoom out enough that we can see the slant. Let's hit graph. This is just zoom 6 right now. Okay, does it look like you can see a slant in that picture? Well, I definitely see the slant like on the left side. It's about like that. So it's going to get closer and closer and closer on the left. But are we really seeing it on the right yet?
No.
No. So probably what's going to happen is this piece up here is going to start to curve back and get closer. To check that, we need to zoom up a little bit higher. Okay, so let's set the y max to, well, let's change the x and the y. Let's set that to 20. And let's set the y max to 25. And hopefully we can draw in a line and start to see something getting closer on the right side. Let me get rid of that. Okay, now I can start seeing it curving back. So it looks like we're going to have a horizontal, a slant. I would say it's something. Let me make it a little thinner. Let's do this one. All right, let's try now. There we go. All right, so maybe about like this. I'll just put that. Well, still can't see it. All right, let's zoom out more. That's not good. Let's set the X max to, I don't know, let's go like 35, and let's set the Y max to like 45. It should be curving closer back to that line. All right, I think we're gonna be able to see it now. Okay, let's put that there and draw our line. That. Keeps changing the size. All right. Well, I think it's good enough. But what do you think now? Does it look like it's starting to curve? It's probably going to curve a little bit more, but it look like it's getting closer and closer. Yeah. If I fix it a little bit, make it a little bit better, and then reposition it, I mean, it's getting there. It's getting closer and closer. So I can definitely see the slant. Okay, so that's a good window for that one. Now, is there anything else in that graph that we might want to check out a little closer? Something that looks kind of suspicious. Like we got to maybe zoom in to see a little more detail.
I think crosses
Crosses where?
at just at 6 or 4.
6. 1, 2, 3, 4, 5, 6 over here.
I think so.
The blue looks like it's close to that.
Oh, I mean, like no.
It kind of stops at the x-axis.
Oh, where it crosses the asymptote? Yeah, it is going to cross it somewhere. I see what you're saying there. That we can tell. It does cross it. But there's something else in that graph I need to check out a little closer.
It's kind of stopping at the x-axis.
It looks like it's very flat on the x-axis. So what I want to do is check out that. That looks like it's about negative 4 to 1 and negative 1 to 1. Let's zoom in on just that box and see what's going on. So I'm doing negative 3 to 1 and negative 1 to 1. Okay. There's nothing wrong with that first window. That first window is good. It shows a complete graph of the big picture. So we need that. But I think we need to also have a separate window. Oh, did I put the wrong thing in?
Yeah.
What did I put in? Negative 3. I think we're going to need a separate window that just shows what's happening in this section. All right, so we can kind of see it better. What does it look like is happening?
It's crossing the x-axis.
Yeah, it looks like it is crossing. So what I want to do now, I don't care about zooming any more on the x-axis, but I want to zoom in more on the y. I'm already at what? 1 and... So let's go 0.1 to negative 0.1. Right? Let's zoom in even more and see what happens. So negative 0.1 and 0.1. And let's see what that looks like. Okay, now I think we're seeing a pretty good picture. So when we look at that, how many times does that cross the x-axis?
Twice.
4 times. Yeah. You definitely can't see it when you look at the big picture. You need to look at the big picture to see all the detail, especially this other piece. But the other window that you need for this problem is this window right here. So the answer to this problem is you need 2 windows to see everything that's really happening.
Was
The big detail.
there going to be something like that on the test where you need multiple windows?
So the point to this problem is you may have to zoom in or out to see what's happening. Yes. Like if I said to you, like how many times does it cross the x-axis? You're not going to see it from that graph. But if I said to you, how many pieces is this graph broken into? Well, you can't see it from this because you're too zoomed in now. You got to zoom back out to see this piece down here. So yeah, you're going to have to zoom in and out to maybe see different things. All right. So that's the homework for tonight. Okay, on page 235. We'll go over that tomorrow, and then the plan is to have review everything we did for this week in class. So the review guide that's online, that might be a good thing to use as your study sheet on the test.